So here we go with a recap of what we learned in class. We talked about work. We started work right after torque. And remember when we were figuring out torque, we took force and multiplied it by the lever arm or distance. We called it lever arm or distance. So that was newtons times meters. Work is very similar to it. It is also a product of force and displacement. Like distance, you can think about it that way. If a force is applied to an object and as a result of that, an object moves, then work is done. Now, mind you, you can be applying a force using your energy, like holding something very, very heavy. You're applying the force, but it's not moving. The object is not moving. You're technically not doing any work. For us to say that work is done in physics, we need to have a force that is applied to an object and the object is moving. In that case, the force is going to be doing work, unless that force is directed a certain way. In this slide, you can see we have our Sir Isaac Newton right here, and we have his picture here because the units of force are named after Isaac Newton. And on the right, we have Joule. Joule's name is used for measuring work and energy. You probably remember that from chemistry, all those wonderful joules of energy. As I said, we can be doing work if something is moving. And in this slide, you can see that while the person is applying the force upward and the weight is going up, this person is doing positive work. However, the force of gravity, let's say he is lifting that with a constant speed. If he's lifting that with a constant speed, I can say for sure that his force is equal to the force of gravity on this weight. But is it positive? Is gravity doing positive work on it? Probably not. Then here, in this case, the force from the person is upward and the displacement is downward. Again, is it positive work? Is it negative work? And then the third case, we have the lady applying her forces now at an angle to the displacement. If you think about if she was applying that force strictly horizontally and the displacement was horizontal, kind of like here, the force is strictly in the direction of the displacement. Work actually doesn't depend only on the force and the displacement. It also depends on the angle between the two. So the full formula for work is this force times displacement times the cosine of theta, and theta is the angle between these two, between the force and the direction of displacement or direction of motion. Another way to calculate it, to find the component of the force that is parallel to the displacement. So in this case, we are showing this is the parallel component. And that parallel component I can find as this force times the cosine of the angle theta. Remember your trigonometry. And there you go. Or you can do that force itself, displacement itself, and then the cosine of the angle between them. Now, the things to remember, certain forces will be doing zero work. Like if the object is moving horizontally along a horizontal surface, then gravity is going to be doing zero work. Normal force is going to be doing zero work because they are at the 90-degree angle to the surface. Parallel forces are going to be doing work in full, if you will, because they are at the angle of zero. They're in the same direction as the displacement. So the force and displacement are in the same direction. There we go. And then the force of kinetic friction is always going to be doing negative work because it's always in the opposite direction of displacement. Static friction is not always that, but this is just for kinetic friction. So let's take a look-see at this one. If the force applied by the lady is 45 newtons, there we go, then at the angle of 50 degrees, we're going to find the work done by that lady as 45 times displacement, which is 75, times cosine of 50 degrees. Plug all of that in your calculator and figure out what it is. I will leave you to it. Meanwhile, I'm going to go over this new example here. We are asked to find net work and the work on each force exerted on the object. So let's start with drawing those forces. So work of gravity equals work of normal force, and it equals 0 because of cosine of 90, which is 0. So we got that one. Done that. Force of pull, because it's pulled in the direction of displacement, it's going this way. Its cosine of 0 being 1, I just can do 120 for the force, 8 for the displacement, and that gets me 960 joules. Remember, it's no longer newtons times meters, it's joules for the unit of work. Work of friction is going to be force of friction times displacement and times cosine of 180. That is because the displacement is to the right, but force of friction is to the left. So work of friction is going to be mu, which is 0.4, times mass, which is 25, times 9.8. Because remember, what is force of friction? Force of friction, our good old formula, is going to be mu kinetic times normal force, which is going to be mu mg when it is flat like that. And then, so that's right here is our force, times displacement, which is 8 meters, times cosine of 180. You're welcome to write that, or just put this minus in front of it, plug that into your calculator, and you're going to get your joules. When you get your two works, the net work will be equal to the change in kinetic energy, and the net work in our case is going to be 176 joules of energy. That is kinetic energy final, because change in kinetic energy is kinetic energy final minus kinetic energy initial. Now, kinetic energy is the energy of motion. Something has to be moving for us to be talking about kinetic energy. So the formula for kinetic energy goes as mv squared divided by 2, where m is mass, v is speed. It's always positive. It will never be negative. Even if you go south or west, it doesn't matter because you're going to square your speed and it's going to be a positive number. So let's say I have a 1 kilogram object moving at 5 meters per second and a 2 kilogram object moving at the same speed. You can guess that it's going to be double the kinetic energy because mass is double. And I can calculate it as 1 times 25 over 2, and that's going to be 12.5 joules. But if it's a 2 kilogram object, that's going to be 2 times 25 over 2, and that's going to be 25 joules. Now, what if the speed is double? What's going to happen to kinetic energy? Is it going to be double? So I'm going to go again with my trusty 2 kilograms, moving at 5 meters per second, and I'm going to double that and go 2 kilograms moving at 10 meters per second. What's going to happen with energy in this case? If I have 25 joules moving at 5 meters per second, then what is it going to be at 10 meters per second? Well, interestingly enough, it's going to be 2 times 100 over 2. Now, what is the difference between 25 and 100? That's a quarter, and that's $1, 4 times. So, interestingly, when I double the V, but I square that, that becomes 4V squared. So, in the formula for kinetic energy, which is mv squared over 2, if the mass is doubled, then it's going to be 2 mass v squared over 2, and that's going to be double the energy. However, if we double the speed, we're going to have m2 with v is squared, and 2 squared is going to be 4. So if you double the speed, you quadruple the kinetic energy, and so on and so forth. I will see you in the next video for the next problem. Thank you for watching, and thank you for studying.